So, returning to the list of things to do in this course, we have already discussed the algorithmic concepts, and of course this is something that we need to spend quite a lot of time on. It is the biggest theme of what we're doing in this course. But let me at least give you an idea of what remains then. So the visualization component and with visualization week that we're going to reach in the third week of the course, I guess that's fairly self-explanatory, and we've already seen examples when we looked, for instance, at the prime number theorem. We used the visualization tools in Maple to aid us in understanding various kinds of mathematical behavior. So this is, of course, an extremely basic thing, that when we're trying to understand some data that comes out of an experiment, we can very often get to a better understanding of this data by plotting it, or in other ways trying to visualize it for the human eye to understand it better. And of course there's a lot of things to keep in mind while doing this, and so this is something that we're going to discuss. Another theme is pseudo randomness, and pseudo randomness is perhaps a little bit surprising subject to bring up in a course of this nature, but it actually turns out to be an extremely important thing. So by pseudo randomness I mean that I'm going to use randomness to make my experiments more efficient. And randomness, true randomness, is like, you know, what you get by rolling a die or something like that. That doesn't really appear in a computer. That's a very difficult thing to have. So you're using pseudo randomness, which is something that is actually completely deterministic, but behaves in a way that is impossible to distinguish from something which is random. This is going to be very important. We're going to discuss how this is done. But the purpose is almost always, in situations like this, to make algorithms more efficient, hence to try to get more information out that we can use for the experiments. And actually I already used pseudo randomness in a way that is a little bit hidden in what I've already showed you. But if you're looking down here, and I was checking the primality of the of some Fermat numbers. Actually, if you would check the specification of is prime that is built into Maple, is that this is actually not an exact algorithm. It's one that uses randomness. So when Maple claims that F13 is a composite number, it's actually not because Maple knows a factor of this number, but it's because Maple has applied some algorithms using randomness which indicate with a very high probability that this number is composite rather than prime. So these ways of thinking also, for instance, when you're doing an experiment on some universe of information which is too big, then you can use randomness to pull out some random elements and look at those. These are the kinds of things that we need to discuss, and this is the theme of the fifth week. And then finally there's the issue of symbolic inversion and linear algebra and graph theory. So the seventh chapter, I guess, is quite self-explanatory. We're going to address some issues from linear algebra and graph theory that just very often come up in experiments, and so this will be something that you probably know quite a lot about, the linear algebra part at least, but we are also going to show you how to do this in Maple, which has some nice built-in packages and so on. But the final issue here is symbolic inversion, and let me end by explaining, or at least giving you an idea of what that is. And essentially, symbolic inversion is one of the most important tools in the toolbox of the experimental mathematician. It is the tools that will help you recognize data that comes out of an experiment in terms of more deeper mathematical understanding. Right? So for instance, suppose that I made a computation and I got this number, like 1.7724538851. That's not very helpful. I mean, that's just a number and it's a little bit unclear precisely what that number is. So if we somehow had a way of recognizing this number, that would be very helpful. Or suppose that I computed some integers like 1, 2, 5, 12, 32, 94, and so on. If there was some way to recognize these numbers, to, for instance, come up with a formula for them or some sort of description of them, this of course would be very helpful. Now, it's a fundamental issue when you're trying to do symbolic inversion that what you're doing is not very scientific, because for instance, if you have the number 1.77 and so on, I mean, this is just 9 digits of some number, presumably irrational, and we only know a little bit of a segment of it, so of course we only have an approximation. So it doesn't mathematically make sense to answer the question, what is this, right? I mean, it's what it is. There's nothing more to say. But we can interpret this question in order to say something like, is there close to this number an interesting mathematical constant? And the same with this sequence here. I mean, we have no idea what the next term is, but if there was some sort of interesting or well-known sequence that was the same as this one to begin with, then we would be interested in knowing this. So symbolic inversion is a very sort of non-scientific thing, but it turns out that, or maybe I should say a non-mathematical thing, but it turns out that when you try to answer questions of this nature, there's a lot of math that you can do. And this is something which is really essential for the experimental mathematician, and is something that we're going to discuss at length. So just to give you a quick idea, if we had these numbers, so what was the number that I wrote down? 1.7724538851. This is the number. There is something built into Maple which is called identify. And identify can take a number like this and say, well, this looks a lot like square root of pi. Right, so if we compute the square root of pi, so what I mean by that is if we compute floating point approximation of it, you can see that it coincides with these numbers. But of course, that's just 10 digits, right? So there's much more information in the square root of pi, and we can't really know for sure that this number is supposed to be a square root of pi. But if somehow this turns out to be probable, this is useful in the processing of a mathematical experiment, because of course it's much more useful to know that the square root of pi is coming up rather than this number here, right? And we're actually I'm going to explain to you how identify works, because it's actually a key tool in experimental math to sort of be able to analyze numbers of this kind, and identify, which is sort of the most basic method, is not always enough. So this is one thing that we're going to look at. When it comes to sequences like this, there's also some tools built into Maple, but I'm not going to explain that right now. Instead, let me show you something which is called the Handbook of Integer Sequences. So this is a book containing essentially a bunch of integer sequences, right? So it looks something like this. I don't know if you can see it, but essentially you look up integer sequences in a kind of lexicographic way. And actually the sequence 1, 2, 5, 12 and so on is in this book. It's entry number 556. And when you look in this book, you'll get a reference to a certain paper, and that paper then explains one way of generating these numbers, and then depending on your situation, you can you can perhaps prove that the numbers that you're interested in are the same as these numbers, and then of course you have access to a lot of information. Of course, this book is from the 70s. Of course, these days you would use something electronic, and what we are going to use is the so-called online Encyclopedia of Integer Sequences, where you can look something like this up. So I will just type these in. It seems to know a little bit of what I have, and then you search, and in this case you get this sequence here, and down here somewhere, actually there's 2 hits, and both of them work with the wonder if they're actually the same. Looks like they might be precisely the same. Anyway, what's very interesting at this point is that here you will find the reference to a certain paper, and that paper then you can go and look up in a math library, and that will tell you something about the sequence that would have required a lot of work to generate from scratch. So this is the essence of symbolic inversion. Essentially, you have some data coming out of an experiment, and then you're asking either a computer program or a database to somehow help you analyze this information.